Welcome everybody. So today we are finishing chapter 2 about Heaps generating function. So we have seen last time the inversion formula and extension numerator divided by denominator. This was the first basic lemma. Today it will be the second basic lemma, the logarithmic lemma. So I need to define this lemma, and to prove it, I need the idea of a derivative in the class of combinatorial object. So I have remind you in this chapter about the general definition of a combinatorial object, the sum, the product, and today we are going to see the derivative of such combinatorial object. So I remind you the general definition of a class of combinatorial objects. So I have A is a finite or enumerable set, and on this set I put a weight, a valuation, which send any elements of this set onto a certain polynomial in variable x and coefficient in k. So very often it's just a monomial t power something, q power something. And to be able to do some operation and generating function of such combinatorial object, then I will I remind you, I have defined the condition star. Star is that if you take any monomial in this ring of polynomial, then I define A index W, the set of all the combinatorial object in A, such that the coefficient of W in V alpha is different of 0. So I am taking all the combinatorial objects which contribute to the coefficient of W. And I suppose that this set is finite for any monomial W. And so with this condition, I can say that the family of weight is summable in the sense we have seen for formal variables. It means that I can define the generating function of such class of combinatorial object to be the sum over all objects of their weight. And you see, when you take this infinite sum, then if you are looking the coefficient of W, then a finite number of objects will contribute to W, so this coefficient will be well defined. If the coefficient is t power n, for example, then there is a finite number of objects which give you a coefficient, the weight t power n. So this was just to remind you this. I have already explained this in the beginning of this chapter, and this was, I am just really recalling what I have done last year on formalization of ordinary generating function. And today we will also have, at the second half of this talk, have the formalization of generating function in an exponential form. So for example, we will see today this fundamental example that the weight of the object will be a second weight multiplied by t power something. I put 2 bar alpha. It means it may be if the object is, for example, made a graph or a permutation, then alpha will be the number of elements of the object. It will be the number of points, the number of edges, etc. But in a very abstract way, I can put any function. I can say the abstract size of alpha. It's any function which can be written like this. The weight of an element in A is going to be another weight multiplied by t power something. And the condition is that all the objects giving a certain t power n, there will be a finite number of objects giving a contribution to this monomial t power n. Yes, t is a single variable, and W of alpha does not contain, the variable does not contain t. So I have a special variable t, which in the exponent n, this is an abstract notation. I call this abstract size of the object. Even if there is no size at all, usually there is a size. There is a number of points, number of edges, number of this. But you can just make an axiomatic of size of the object by saying the weight is like this, and I call n alpha between 2 bar means the size of the object. So to define the derivative, which is fundamental for this lecture, alpha to A.
No, all alpha such that alpha equals to n.
Right. A(n),
Okay, n is all alpha.
A index n. For an integer n, I call all the alpha satisfying this. So this must be finite.
We are defining new weight with the help of other weight.
Right. Yes, a new V. W is another weight, which is some which is a monomial in some formal variable with coefficient in k. But this monomial, the formal variable, does not contain t. If I go back to the here, you see, the weight is with variable in x. Now x will be a certain alphabet y plus disjoint with a variable t. T is an extra special variable, and which x equal t plus another alphabet y. So I take the definition. I am going to define what is a pointed object. You have a certain object, I want to point. So this is abstract definition, that the pointed object, so it's a new class of object with a C and a new valuation. And C, the set of objects, is a disjoint union of all this product an cross multiplied by one, like the segment 1n. Which means is the object of the pointed is just, you take an object of in A, in the first class. This object has a weight like this, so it gives you an n. And then you take any integer between 1 and n. So in the case your object is exactly n points, the size is a number of points. Pointing means you are going to specify one of the points, one of the vertices. But we are doing in an abstract way to define in a very general way what is a combinatorial object and what is a pointed combinatorial object. It's just a pair like this. You take a alpha in an with a size n, and then you choose any integer between 1 and n. And of course, the weight does not depend on the index you choose. It's the same weight. Vc of gamma equal Va of alpha. So the weight does not depend on which integer you choose between 1 and n.
So the idea is that if the weight represents the number of pieces, you're choosing a piece.
Yes. So it is the abstraction of the very natural things, like you take a graph. Pointed graph means you specify one of the vertices. You take a permutation, and you will specify one of the vertices of the permutation. You take a path, you take a cycle, you will specify maybe one of the edges or maybe one of the points. It depends of the context in which we are working. But this is nice because it gives you an abstract definition for the general class of object, according only to this condition that there is a special variable t that I extract from the weight. And now the lemma tell you that the generating function, ordinary generating function for pointed object is t times the derivative of the object itself. This gives you kind of interpretation, of formalization in terms of the level of combinatorial object, a formalization of the derivative in formal power series. In fact, it's t times the derivative. So proof, you take the derivative function of the object is this, which I'm going to specify. The weight is, there is an integer n. So I specify the sum over all n, and then sum over all object having the size n. Okay. Then what is the derivative? The derivative function of a point, of the pointed object, is the sum over all these pair, gamma. I is any indices between 1 and n. This is the definition of the pointed object. And the weight is the same. The weight of gamma is the weight of alpha. And so this is, this term is w of alpha t power n. And now the choice of an index, for any n, I have n possible choice. So this means I just multiply by n here. And so if you take the derivative of this, it's going to be t power n minus 1, n times t power n minus 1, but you have remultiply by t to get back the coefficient tn. So I get the derivative function of a point. It's the derivative of this derivative function multiplied by t. So it's very elementary calculus. This reflects this notion of derivative, of pointing an object, reflects the idea of derivative. But in ordinary derivative function, you have this t times the derivative.
So then this pointed thing, the empty object,
No, it's zero, yes.
So you eliminate the empty object.
Yes.
Normally, if you want.
T is t power 0. No, it's eliminated. It's 0, and I cannot choose any indices. If there is no vertex, I cannot point any vertex. So once I have stated this abstract derivative of combinatorial objects, now I can state the logarithmic lemma. So now we have a weight. We go back to heap of pieces. Heaps of pieces, the weight of a heap is given by the weight of the basic piece. Now the weight of a basic piece is going to be of this form. There is a t, variable t, so t is going to count the number of pieces. The extra variable is just t for a piece. And so the weight of a heap is a product of all the weight of the basic piece, independent of the level, multiplied by t power. So this means now the number of elements of the heap. My variable t is counting how many pieces in the heap, plus some extra weight, which does not contain t. So now the logarithmic lemma tell you the following. That t times the derivative of the logarithm of generating function of heap, the ordinary generative function with the t, is equal to sigma over all pyramid, generative function of pyramid. So I remind you, a pyramid is a heap with only one maximal piece. So in other words, taking a pyramid is, roughly speaking, taking the t times the derivative of the logarithm of the generative function of heap. The log of heap, taking the logarithm, roughly speaking, is going to pyramid. So I'm going to give a proof on a visual example, visual proof. So visual proof here is a kind of heap. And I am pointing one of the elements. I am taking the pointed combinatorial object. And when you point, well, there is a poset. There is a poset behind the heap. And you feel I am going to push down the blue dimers. Some dimers are going to be embarked as usual. It's an elementary operator I will use many, many times in the class. So it's equivalent in term correct. It should I should say that if I take x, there is an ideal generated by x in the poset underlying the heap. And this ideal, so it's a pyramid. Ideal, I recall you in a poset. It's all the elements y in the heap which are less or equal to x. So this is, you see, this is the ideal, all the elements below blue for the poset. So intuitively, it corresponds to take the blue pieces and push him down. So like this, you see, if you push down, then the pyramid is extracted from the heap. And what remains, so what remains above is another heap. And in fact, when I extract my pyramid, I have decomposed my heap, a product, as a product of heap, into two heaps. And so you have easily, you prove that this equality, in terms of product of heap, a pointed heap, means a heap with one of the pieces is pointed, is equal to a pyramid multiplied by a heap. So it's an equality in the heap monoid, which is very easy to prove. But once we have this notion of a pushing, or which is equivalent to taking an ideal, and what remains is there is a poset related to a heap. And so what I translate this now in terms of generating function. Pointer in heap means t times the derivative. I call y the generating function of heaps is equal to z. Z, I call z the generating function of pyramid multiplied by y equal heap. So this equality between in the heap monoid is projected into an equality on generating function. And now t times y prime divided by y, it's t times the logarithmic derivative. So logarithmic derivative is equal to generating function of pyramid. Okay, this t y prime divided by y equals z. So I have this equality, which is this equality. So that proves this is a proof of the simple logarithmic lemma. So this is one form of the logarithmic lemma is t times the derivative of the log equal sum of pyramids. Or I can put this in an equivalent form. If you don't like the t times the derivative, equivalent form is the logarithm of generating function of heaps with t power the number of pieces of the heap is equal to the generating function, where this is the number of elements of the pyramid. Because if you take the derivative of this is going to, if I call this n, this will be n times t power n minus 1. If n is the number of pieces, and multiply by t, give you this equality. So this is easily equivalent to this. So the logarithm of heap is generating function of pyramid, but there is a slight, it's not exactly pyramid, it's pyramid when you divide the coefficient of t power n by the number of elements of the pyramid.
You've done integration.
Or integration. If you integrate this, then you go back to the previous, because integration is a reverse function of the derivative. Okay, there is also some abstract combinatorial object. You can define the integral of an object, but it's better to work with exponential generating function to have the integral instead of ordinary generating function.
How did you get this without integration?
Oh, it's in terms of function of t. It's if you integrate this, but at the level of quantum object, there is no integration. You need exponential generating function to define integral of a quantum object. And this is another story. But in terms of the analytic level, in terms of power theory, of course, if you integrate this, you get back this. If I take the derivative of this in both sides, then now from the inversion lemma, this is equivalent also to logarithm minus logarithm of the generating function of trivial heaps. So this will be very interesting in physics, because this is a partition function of gas model. And so taking the inverse, taking minus this is equivalent to taking the log of the inverse. And taking the inverse, you go to pyramid, then physicists, that's exactly what they do. They took t times the derivative of the partition function. So we are in good harmony with physics. You will see this in the part with connection with physics. Suresh is very it's standard material. So this is one form of the logarithmic lemma series. So now we have an extension of the logarithmic lemma, a more general form, which will be very useful when I will do chapter 4. It will be to show the relationship between heaps of pieces, all these basic lemma, the 3 basic lemma, and we will reprove, interpret this, all the classical theorem of linear algebra, we will reprove with heaps of pieces. Cayley-Hamilton inversion, Jacobi, McMahon, there is many theorems. Everything can be put in the same roof with heaps and this lemma. So maybe I will need this more general form to take the logarithm of a heap. So the more general form is the weight of a piece. Instead of being v of alpha multiplied by t was the variable counting the number of elements of the heap, I am taking something more general, t power something. So which means that a piece may contain, t is going to count some number of elements inside the basic piece. So we will make very often, when we take heaps of segment, heaps of cycle, heaps of many things, I am going to count according to the number of vertices, edges of the basic piece. So t is not counting the piece itself, but something more specific inside the basic piece. And I need to take the logarithm of this, especially in the connection in the second part of this course. So now the weight of a heap. What is the weight of a heap? It's just as usual, it's a product of the weight of the projection, t times now I call L of E. It can be the length, you can think of L as a length, or is the sum of all the L of the projection of the piece of the heap. So each pieces of a heap, see, there is certain integer, the L of the piece, and to take the sum of all this integer. So when we were counting the number, when L of E, L was 1, then L of E is the number of pieces, the previous lemma. And then I call H the class of all weighted heaps with this weight. So this is a heap, there is a weight V like this. And I suppose it satisfies this condition so that I can get some summable family, I can get some talk about this generating function of the sum of the weight of the heaps. Yes. This is L of pi of x, yes. No, this is a definition. L of E. I define the L of E. The L of E is a sum of all the L of each of these pieces, but the L of a piece, element of the heap, is the L, in fact, of the projection.
Actually outside the product.
Look at the weight of it. See, this is the weight of a basic piece. This is the weight of a basic piece. So the weight of an element of the heap will be the weight of the projection, which will be the projection of the heap multiplied by TL of the basic piece. So you see, so the weight of the heap is the projection, it's the weight, the product over all pieces, the weight of the projection, and T power L of E, where I define L of E to be the sum of all the L of each projection of the pieces.
L of x, maybe?
L of P of x for all x. X is a...
Oh, it's outside the product.
So in the first line there's a
Bracket, yeah. E is a heap. In the heap, you take all the pieces.
So
you
x-
put L of x inside the bracket.
X is a pair alpha I. X is it's one element of the heap. It's a pair alpha I. So the projection of X is alpha, in fact. And I take by definition, the L of the E. By definition, it will be, because the weight of a heap is a product of all the weight of elementary pieces. Each pieces will have a T power something. So the total weight will be T power, the sum of all the exponents. Okay? No problem? I can... everybody follow? So H, I will call this class of weighted heap, and I suppose it satisfies my condition to be able to write a formal sum, the sum of all the weight of all the heap. So this will be a class of combinatorial object. As the abstract class, you see, I have my weighted heap with satisfying the condition star. So with this abstract class, I can take the pointed class, as I have defined before. What means a pointed class? Pointed class is it's a pair, you have a heap, and an integer j which is between 1 and L of E. Where L of E, you see, is the sum of all the L of the projection of the element of the heap. Maybe to imagine a visualization of this abstract definition, take a heap of segment. Like this, take the L, function L will be the number of cells of the segment. So you see, this is a 3 element, 4 elements, so each segment in the heap, L of the segment is the number of cells. And pointed heap means I am pointing one of the cells or one of the pieces. Because I am taking an index I, which is between 1 and the L of E. L of E is the sum of all these L of pieces. So the sum of all these pieces, you have to point one of the elements. But I have to say, okay, abstractly when I was here, J was between 1 and L of E. So you have to transform this index J to say, okay, J is going to be the choice of a piece in the heap, and the choice of the integer for this piece between 1 and L of this piece. So which means I have to split my interval 1 L of E into different intervals. This is big interval, the sum of all the L of each pieces. You can think of this as the length of all the segments. This sum, I am going to put it as a disjunct union of first segment, the first pieces, and the second pieces, which is of length, abstract length x2, etc., etc. So all these segments here, I decompose them as a segment, and you have to choose an index between 1 and L of E. You have to choose something in one of these segments, an integer inside one of these segments. So I have to make a convention to order the pieces, this segment. You have to order them in a certain way. When you go back here, you see you have to say, okay, this was the first segment, second segment, third segment, etc. You have to make an order in different segments, which give you a segment in integer 1 L of the pieces, give an order, and then you choose one of the index between 1 and the L of the total heap. We'll be choosing a piece, and inside the piece, choosing an index. So maybe the most convenient way is to take the linear extension of E. We have seen the normal form. Take the linear extension and relate it to the lexicographic normal form. So there is a total order, a canonical total order on the pieces of the heap. And for these pieces, then you total order on the element of E. So this is the first element, the second, etc. And for the first element x1, then you put the first segment, and second element x2, you put this segment, etc., etc. So you are dividing this big segment into the union of consecutive segments. Each segment corresponds to one of the pieces, and these segments are totally ordered by the lexicographic order of we have seen before, or sometimes it's called the Knut normal form. And then choosing an index between 1 and L of E will be equivalent to choosing an index, choosing first a segment, and inside the segment you choose an index. So if you have the example of heaps of segments, see maybe for the lexicographic normal form, this is the first one, the first minimal piece, the leftmost minimal piece, then the second one will be this one, then this one, then this one, then this one, etc. So you have a unique decomposition of your segment 1 L of E into this segment, and then I have chosen this. Pointing the heaps means pointing a piece plus the choice of here is the choice of a cell. There is 4 cells, but in an abstract way, the choice of something between 1 and L of the piece, the abstract length of the piece. And then again, you push down this segment, and you get a unique decomposition. This is now a pointed pyramid. So the pyramid is still pointed. It's not, before it was just a pyramid because I was just considering L of the piece was 1. T was the variable giving the piece. Now T is a more complex variable. I will need this in the following chapter. So you take this piece containing the point, you push down, you get what I call a pointed pyramid, and what remains is a general heap. So you get this equality. T equal pointing a heap in terms of the abstract combinatorial object. the pointed heaps is equal to the product of pointed pyramid multiplied by h, where pointed pyramid means you are pointing the maximal piece, unique maximal piece of the pyramid. So you get this equality, where y is the logarithmic, y prime over y is the logarithmic derivative of h, but z now is a generating function of pointed pyramid, so which I can write this way. So the new, more general form of the logarithmic lemma, the left member is exactly the same, but the right member is a little more complicated. Instead of having pyramid, you have pointed pyramid. So I go back to abstract level of quantum object. What means a pointed pyramid? It means a pair pyramid and an integer j, where j is a choice of an integer between L1 and the L of m, where m is the maximal piece of the pyramid. So for my heap of segment, you see, pointed heaps of segment would be pointed pyramid of segment. There is only one segment at the top of the heap. In this segment, there is cell, and you are choosing one of the cells. And this is the abstract form. There is no cell, nothing. There is just a function, an abstract length or abstract size of the maximal piece. Now I can go back again by a kind of integration. I can delete, cancel t times derivative, and what I get is this now. You have to t times, you divide by L of p. So this is another form, the logarithm of the heap, where t, the variable, is something more complex than just counting the number of pieces, is the generative function of pyramid, t power of the L of p, but dividing L of p with pointed pyramid. Of course, if you take the derivative, you get back this, taking the integral, you get this. So a nice example which will remain in many chapters, in the next chapter, the next two chapters, and then in relation with physics. So it will be used many, many times. It will be heaps of cycles on a set. So the basic piece are cycle on the set X. It's what is a cycle? It's in graph theory, you see in graph cycle. In graph theory, you have an elementary circuit. A circuit is a path, sequence of points going back to the origin. Elementary circuit means that all the vertices are distinct. So this is an elementary circuit starting at S0 and ending in Sn, and I call cycle elementary circuit up to a circular permutation of the vertices. This is a cycle which appears when you look at permutation as a decomposition in the cycle notation. And the L of a cycle is the number of vertices of the cycle, also the number, the length, the number of edges. The number of edges is 4, it's the same as the number of vertices. So this is below L of the cycle, the length or the number of vertices. So in graph theory, maybe cycle is another definition, but here, all the class, I will use cycle because it's cycle of a permutation. It's a standard. Also, you can say in terms of words, if a sequence of different distinct letters is what the elementary circuit here. So you have a sequence of distinct letters with Sn equal to 0. I have a word, and cycle also taking a sequence up to a circular permutation is equivalent to take an equivalence class of conjugation in terms of word, where two words are conjugate. If and only if you can write one word as uv and w prime as vu. This is a conjugation in terms of words. One word is uv, the other word is vu, and this is an equivalence relation. That means if you have again another word which can be deduced from w prime by cutting into and reversing the two parts, then this third word W double prime can be obtained the same way from W. You can check that this relation is an equivalence relation, and it's the conjugate class of a word, the class of conjugate zones. So a cycle is a conjugate class of the word obtained by following the element of an elementary circuit. So it depends which formulation you like the best, conjugation of word or defining a circuit up to circular permutation. So let's take now the logarithm, you see. On this example, what is the logarithm of a heaps of cycle? So the heaps of cycle, what is the dependency relation? It's the support. The support means the underlying vertices of the cycle. The two supports of two cycles are non-empty intersection. If two cycles have some common vertex, this is a dependency relation. And we will work many times with the consideration of heaps of cycle. In the paper, so this is for Suresh in string theory, the paper I was referring. There is a lot of heaps of cycle in this paper, and this is equivalent to rearrangement. We'll see this in the next chapter. So it is heaps of cycle, you see, and taking the logarithm of a heaps of cycle, but logarithm with a variable t, the L of E. L of E is the total number of vertices of all the cycle of all the heap. If I was taking t, the number of cycles, this would be a different expression. Now I will take the logarithm of this generating function, and then I will get what I will get. I will take this will be the general logarithmic lemma, the sum over all pointed pyramid of cycle with this t powers this divided by this L of p, and pointed pyramid of cycle. What it means? It means like this. There is this picture. There is only one maximal piece. There is only one cycle on the top of the heap. And pointed means that you are pointing one of the vertex of the cycle. So this vertex pointed x, sorry, it's x is sometimes it's designed a vertex, sometimes it's designed a piece. So this vertex belongs to the maximum cycle of the pyramid. So this is a pointed pyramid. So you see an example of the general
What is the trivial heap related to this all set partition?
trivial heap.
Related to this heap of cycle.
So trivial 2x2 division cycle. This will be the last slide of the course. Trivial heaps of cycle will be related to determinant.
Set partition.
No. Wait, the conclusion will be the transition with the next course. It's going to be the determinant of 1 minus a certain matrix. So this generative function heaps of cycle will be the inverse of generative function of trivial heaps of cycle, and trivial heaps of cycle is exactly the determinant of 1 minus a certain matrix. Yes, a question? Only one vertex of the top cycle. A pyramid means there is only one maximal piece. Pyramid, there is only one maximal piece. Maximal piece means maximum element for the underlying poset, or in terms of visual heaps, it means you take the piece and you can evaporate it without touching any other pieces. So in terms of commutation monoid, it means in an equivalence class, you can bring these letters as a cycle at the last letters of the word. They call this terminal alphabet. Terminal alphabet is a maximal piece, and pyramid, only one maximal piece. And pointed pyramids mean I am pointing one vertex of the maximum cycle. Only one.
Any vertex can become like a last because you are taking up to permutation. No, if I take another vertex, the pyramid makes different.
Yes, it's taken. There is n vertices. Cycle has n vertices, and I am choosing one of the vertex. So there is n possible way. If there is n vertex, n possible way to choose.
It's the same as the pyramid with different pointed you're choosing something.
No, the up to circular permutation means that if you are starting from a point, of the cycle, you follow the vertices, and you get a word. Starting from one of the vertex, follow the vertices of the cycle, you get a word. But I want to forget which point I have started. So this is a cycle. Now pointing the cycle means, okay, I can, from this point, I can follow the cycle and I get a word. Or I can point also an edges. An edge, you can point a vertex, and there is n edges and vertex. But so this seems starting from a point and going back, this is elementary circuit. Cycle is up to a circular permutation. And now pointing the cycle, you go back to your vertex, to your sequence, which is not defined up to a circular permutation.
So, for example, you can just imagine. So you said that T to the, I mean, L of E can just be the number of vertices in each and every cycle added up.
L of E is the total number of vertices in all the heaps of cycle, which is the same as total number of edges. There are many edges. Total number of edges in all this picture is L of E. Total number of vertices in all the cycle. Okay. Now we'll get a second proof of the logarithmic lemma using exponential generating function. So last year I have given a whole chapter on the exponential generating function by working with spaces. So I will remind you, I will make a short summary of what I have said last year, independent of. So this is a way to also to embark in the world of exponential generating function. I will not need very often in the class exponential generating function sometimes, but it's a good maybe for your general combinatorial culture to see how we work with combinatorial exponential generating function. So there is different way of looking in a general setting, but I like the spaces approach of the people from Montreal. So the naive definition of a spaces, you have a finite set, and this set, you have a combinatorial construction. Like, for example, this one. Take a set equal A, B, C, D, E, F, and you can define a tree on this set. A tree is a graph with no cycle. This is the idea. You have a certain set. You can define what is called the spaces, combinatorial spaces, which are trees. But this construction you can have done also on the set of integer 1, 2, 3, 4, 5. I have done this on the set of these vertices. You can do on any other set, which are in bijection with this set. So your construction, you can transport it on another set as soon as you can transport by bijection all this construction. So the naive definition, you see, you have an underlying set, and you have a combinatorial construction of this set, and we call the spaces F. It's just the list of all the structure, all the construction you can do on this set U, and we call this the F-structure. So F-structure is, for example, any trees you can do on the spaces F, which is the spaces of trees on the set U. You just make the list. Or if U is the spaces is permutation, you will give the list of permutation. So this is a kind of abstraction of what we call a combinatorial object, a species, which is going to work with exponential generating function. So graph, partition, set partition, permutation, on the function, trees, everything, all are examples of some spaces. But to be able to define an abstract way, you have to define, if you define all the structure on U, if you have a bijection, then you can transport all the structure you have defined on V. So if you have the list of structure on this, then you can transport it as a list of structure on V. I don't want to go too far in the abstract definition. It should be defined abstractly as a functor of a, but maybe forget this. It just keeps the intuitive idea. It's, for example, the tree, U equal ABC. You have a list of trees. The F structure is, there is 3 trees on the set ABC. Then I get a bijection F between ABC 1 to 3. So I can transport this structure on this. So this defines me a map capital F of small f, which is the bijection between these three trees are going to be in bijection with these three. And there is some axiomatics that the transport is coherent. If you make two transportation by two bijection, then you must have this compatibility between transporting a structure on the set U to another structure on the set V.
And can we do the directed tree if they are so the same, right?
Directed trees, it's a...
In the same way?
Well, as soon as you have a list of elements, it just gives a list. So it just gives a list, and as soon as you get the list on the set and set U, you must be able to give the list on all the set in bijection with U. So for this, I don't want to be too formal to abstract. If you want to have a formal definition, it's functor, everything, but then we lose the beauty of the simplicity of combinatorics. So for this level, maybe just keep this idea of you have a set U and you make a F structure. You have a F, a species. It can be a trees, permutation, a heaps, or anything, and then you put, and then you can define the exponential generating function on this. So the definition is this. You see, if you have an F structure, here is a symbolization of U set U. So usually you would put, you see, an arrow F means I am putting a structure F on this set, and this, the number of elements of this on the set U does not depend of the set itself. It just depends of the number of elements. So you can put your structure F, you can put on the set 1 to n. So an is a number of such structure of the species F on any set with having n element. And then what is defined is the exponential generating function of the species F. So if and which is written like this, F of t, just a parenthesis, the exponential generating function. In the previous slide, you see this was introduced by people in Montreal, Joyal, Labelle, etc. in 1980, a long time ago, and there is a beautiful book, Combinatorial structure and tree-like structure, to explain this. So this is abstraction, an abstract way of looking combinatorial objects which are fit very well with the exponential generating function.
Here it is considered only finite set or even one given infinite set?
U is here it's mainly finite. U is yes, you can make infinite, but then an is no more defined. So you can make, but you have to put weighted species, then you can work with infinite set if it's weighted. But let's take some example. Species of permutation. So here is the underlying set, for example, 1, 2, 3, n. An is n factorial, and exponential generating function is sigma over n factorial tn over n factorial, so it's 1 over 1 minus t. And if you take total order, this is something different as a species, but generating function is the same. So in fact, two species may have the same generating function, but they will be in the term of an abstract term of species, they are not isomorphic. So this is a very easy example, permutation, total order. Cycle, we have seen cycle, heaps of cycle, just a cycle, it's a circular permutation. Its number of such is n minus 1 factorial, circular permutation. So the generating function is sigma of tn over n. It's sigma over n minus 1 factorial divided by n factorial. So you get tn over n, which is the abstract definition of the logarithm of the formal power series. So it is taking the logarithm is going to cycle. I have a species which I will use a lot in this course. It's a species set. Species set means you take the set and you do nothing. The structure, there is only one structure, you do nothing, you take it set itself. And so the generating function, there is only one structure for each. So the generating function, the exponential of t. T plus t2 over factorial plus t3 over factorial 3, etc. So usually in the French-speaking people, we call this E. Because in French, set is ensemble. And also because a beautiful relation, ensemble is E, and the letter E for E power t was invented by Euler, which is also beginning with E. So we like this connection of ensemble, small e, and Leonard Euler. So we'll use these spaces in the logarithmic lemma. So now another example is a partition. Partition is just a partition of a set. The number of partition is the so-called Bell number, Bn, the number of partition of a set. Here is a set partition in 4 different blocks. And the generating function is the exponential of t minus 1. And I will very soon give you a proof of this. So these are the Bell numbers, the number of partition of a set. So once we have defined spaces, here it's example. So we can define some abstract operation. Like for the ordinary generative function, you can define the sum, the product, and the exponential of the spaces. So the sum is just, see, by this picture, if you take an underlying set U, then the sum of F plus G is then else you take an F structure, or else you take a G structure. And of course, the sum, generating function of the sum will be the sum of the generating function. For example, if you take the species set, the species set is the sum of the species even number of elements and the species odd number of elements. You take only the species EP, means you take only, for each set U, you take only one, the set itself, if U is an even number of numbers, and you take nothing if the number of elements is odd. So generating function of this is the hyperbolic CH of t. The sum of all exponential generating function for all the variable t which are only even degree. And this is only odd degree. And of course, e power t is the sum of these two. Yes, a question?
Can we have like F minus t or something?
Minus? This is something, it's possible to make, but this is more, it's virtual, it's called virtual spaces, and even the quotient, this is more, something more, no, I don't want to go at this abstraction of level. So I will need just the sum and the product. So this will be an important operation. So what is, we have two spaces F and G, and what is the product of the two spaces? So an element gamma of this structure gamma of this product. So you take U is this set, underlying set, and an F point G, F multiplied by G structure, like gamma. Gamma is a quadruple. So U1, U2. What is U1, U2? Is a partition of U in 2 blocks. Like this. You see, you have a U1, I have 2 elements here, and U2, 1, 2, 3 elements here. And now I have alpha and beta. Alpha is an F structure on U1. So this is alpha. You see, I have on these 2 points, I put an F structure. And now on this 3 point, which is U2, I put a J structure. So you see the structure of the product is this quadruple, a partition in 2 blocks. And on 1 block, I put an F structure, alpha, and on the second block, I put a G structure, G. And proposition, the generating function, exponential generating function of the F multiplied by G is the product of the 2 exponential generating functions.
But here there is an ambiguity.
Ambiguity?
Like you have selected how the ordering you have put the position.
Where is the ambiguity?
So there are five elements are there.
Yes?
So you have taken the first and fourth is F and the other 3 is G.
Yes?
So why not another 2 combination?
Well, any combination, you take any partition.
So any combination.
It's an, I would say, the order partition. Partition in 2 blocks, U1, U2.
Okay.
So it's I should say, order partition. So there's the first block, second block. The first block, I put an F structure. Second block, I put a G structure.
Okay.
The block can maybe empty. I can have, it's possible to have some structure on the empty set.
Okay.
Usually there is no structure of the empty set, but there is no ambiguity. Huh? So,
Okay, okay. This is coming from this side to this side. Okay.
Mhm.
Okay. So
now, to prove this, just think of the product of generating function in exponential notation. So this means that the coefficient of this product, which is Cn divided by n factorial, is equal to the choice, it's equal to sigma vk over k factorial divided by bn minus k divided by n minus k factorial. See, this equality is equivalent to this product in exponential generating function. Just a 2 line of elementary calculus. If you take the definition of product of two generating functions in exponential form, this is the coefficient of the product is given by this formula. So you see, when we work with ordinary generative functions, there is no binomial coefficient here. Working with exponential generative function gives you binomial coefficient. And why is this formula is true? Is because to take a partition in two blocks means you are choosing k element. U1 is a choice of k element, which is a binomial coefficient. U2 is the remaining element, n minus k element. On the first block, U1, you put alpha structure. There is a k different way to do this. On the second block, you put a G structure. There is b n minus k way to do that. So this gives you a proof of this formula. It's just a choice of this quadruplet. Choice of the order partition into block. Choice of the pair alpha and beta. From this definition, I get this formula, which is equivalent to this formula. So very nice example of this formula. It's derangement. Derangement means it's a permutation having no fixed point. No index I equal to sigma I. And then I can write in terms of product of species any permutation. Here is a permutation in the cycle notation. Here are the cycle of length bigger or equal to 2. Here are the cycle of length 1. This is a fixed point. So to choose on these 3 points, to choose 3 fixed points is equivalent to choose a set. If you take any set, if you do nothing, it's the same as putting a loop to any of this is an isolated point. So this is a species set. This is E here. Now here is a species D. And this means I have a partition in 2 blocks. On one block, I put a derangement. On the second block, I do nothing. I put a set. So I have the species permutation equal D multiplied by E, which in terms of generating function tell you 1 over 1 minus t equal generative function of derangement multiplied by e power t, which I can write like this, which is equivalent to this. And so you deduce that when n, the probability to get a derangement over a permutation, when n go to infinity, the limit is 1 over e. And this was posed a long time ago, in 18th century, as a problem des rencontres, or everybody go to the theater, put a hat before going to the theater, then everybody take back his hat, and what is the probability that nobody get his hat on the head? Probability for a big is 1 over e, and this was a surprising, people were surprised by the appearance of e in this very simple problem des rencontres. So now we have before going back to heaps, I have a second operation which is called substitution of a species into another one. So we have 2 species f and g, and the species g is such that on the empty set there is nobody. The list of structure g on the empty set is empty set. And this is the visual definition of this operation. So you say, you take a partition, take a set U. So and you take a partition of U into class U1, U2, UK, which are non-empty subsets. Like this, you see, I have a partition in 3 subsets. So partitions, the blocks are not ordered. It's an unordered partition. So on each block, you put a J structure. And now on the set of blocks, which unordered set of blocks, which means like U divided the equivalence relation generated by this block, I put an F structure. And usually in French we call this is an F assemblée of G structure. An assembly of people and assembly of blocks where in each block there is a G structure. For example, in permutation is an assembly of cycle. G is a cycle, and F is just a set. There is no, I just exam like this. And then I will go maybe a little fast now. For this operation, the relationship between generating function is that it corresponds to the composition of generating function. And to compose this is equivalent to say this equality. So what does it mean? Here, factorial n divided by factorial n plus 1, factorial n plus 2, factorial n k, this is a choice. This multinomial coefficient is a choice of this order partition. Multinomial coefficient is a choice of partition, but the blocks are ordered. Then divided by k factorial means I am taking the block without the order of the block. I'm taking, and then on the unordered partition, in each block, I put a species G, which is this coefficient, and then the total on the unordered partition, I put an F structure like this. You see, so the number of such structure will be A index K, and each G in each block will be B1, B2, etc. B index and 1, B and 2, B index and K. And you can check that this equality is equivalent to this in exponential generating function, in exponential generating notation. And the particular case that we will use for the logarithmic lemma is that if you take the F species to be the set, you do nothing, then this composition is going to be the exponential of the G structure. So exponential means, you see, you have here is the general case, you have a partition in block. In each block you put a G structure. On the set of block you put an F. The block an order, and for F equal E, then so it means you do nothing, you see. F, you do nothing. So you just take the block, an order. In each block you put a G structure, and what you get is the exponential of the structure F. We call this an assemblée of G structure. And then you get the relationship between the two generating functions is that H is exponential of G. So if you have a generating function, which is interpreted by a certain one of the block, taking the exponential means you take many blocks, and you put in each block, you put a G structure. This gives you the exponential of the generating function. So 2 examples. I go back to the partition Bell number and to the permutation. So B is the partition. So what is B? B is an assembly of non-empty set. See, I take a partition, an order partition. So in each block is non-empty. So the generating function for non-empty set is e power t minus 1. And now I take an assembly of this block, which means I take the exponential of the generating function. So you can very easily find the generating function for Bell number from the general principle that B species partition is exponential of non-empty set. Second example, the permutation. Here is a permutation are the exponential of cycle. When you take a permutation, you take a partition of the vertices, an order partition. On each block, you put a cycle, and you get a permutation. So permutation is exponential of cycle. So here is a generating function of permutation in exponential generating function. Here is a cyclic permutation. The cycle cyclic permutation, there is n minus 1 factorial, so this is Tn over n, which is logarithm of this. So the log of a permutation is a cycle, you see. Or the exponential of this is exactly this. So now you see it's very easy, very convenient operation. In general, taking the logarithm is going to mean, in exponential notation, taking the connected component. Or taking the exponential means you know you have this, then you can repeat many times. For example, if you take the logarithm of the generating function in exponential notation of the graph, number of graph, then you get connected graph. And what we are going to do is to take the logarithm of heaps, but in exponential notation. In logarithm, the connected component, they are not at all connected. The idea of connected, but it will be pyramids. The pyramids for heaps will play the role of cycle for permutation, but in a totally different way, as we are going to see. So also there is some weight, because my heaps are weighted, so everything I have done can be repeated with weight of the species. So with weight, each time you have an operation, it's if you take the product, etc., the weight is going to be the product of the elementary weight of each component of the operation. So I will not insist on this, but putting a weight does not change all this product of derivative function, substitution, exponential. All of this work with the weight. As soon as the weight of component is a product of the weight is a multiplicative function when there exists some component or substitution, etc. And you have the generating function of a weighted species. Instead of being numbers, it's a sum overall between all the weight of all the structure on the set of size n. It's a polynomial. It's a sum of weight as a. So I don't insist. Everything goes through the weight easily from the ordinary exponential generating function. And now I can give a second proof of the logarithmic lemma. So I make a grand detour in the exponential world because it's good for your cultural point of view in combinatorics, and maybe we will use it also in some other exercise or problem to, instead of working with ordinary derivative function, to work with exponential. Sometimes we need really to go to exponential, and you cannot avoid, but here I can, for the logarithm of heaps, I have avoided to do exponential, but it's good to see how it works with exponential generating function. So the second proof with exponential generating function. So take a heap. This is a visualization of the heap. This is, and what I am going to do is to label heap. To work with exponential generating function, I am putting a label 1, 2, 3, 4, 5, n on each element of the heap. So you put the label in any way. So the number of ways to do this, number of ways to put your label is n factorial. For each heap, you multiply by n factorial. This is all possible label heap. So when I work with exponential generative function for label heap, I multiply by n factorial, and then I have Tn divided by n factorial. So, okay, working with ordinary generative function of heaps will be the same as exponential generative function of label heap. And when I have label heap, maybe I can do the logarithm now. So the idea, you see, when you have a label heap, so each species has a label, take the minimum label, which on my picture should be 1. Take the minimum label, take the piece with minimum label, and you push it down. It was here, the 1. What happened? I repeat. Here is the 1. So take the 1, push it down, you see. So take the ideal below the 1, then you get a pyramid, a label pyramid, but the condition, there is a condition, your label are not totally arbitrary. The smallest label, which is the 1, must be the label of the maximum piece. Now I repeat the construction, I take what remains, I take the minimum label, which is 4, and what remains is a pyramid. So I have decomposed my label heaps into the product of 3 label pyramid with a condition for the smallest label on the top. Now you can, it's not necessary to know the exact order of the 3 pyramids. So it's an unordered set of pyramids. If you give me by these 3 pyramids without any order, what is the first, second, and third pyramid, you can reconstruct, this was the first, because 1 was the smallest label of the 3 possible label of the pyramid. Then there was 4, the smallest label. So the smallest label of the 3 pyramid is 1, 4, 7. So you can reconstruct your label heap by taking the product of these 3 pyramids ordered by in the order of the smallest element of each of the maximal piece. And so I can say that I have an assembly of label pyramids satisfying the condition M. Condition M means that the label of the unique maximal piece of the pyramid is the smallest, the minimum of the label of all the pieces of the pyramid. And so in terms of exponential generating function, I have the exponential generating function of heaps, of label heaps, is exponential of the generating function of label pyramid satisfying condition M. Now we have to go back to ordinary generating function by going back to heap. I say from a heap, labeling the heap means there is n factorial way to label the heap, if n is the number of vertices of the heap, divided by n factorial. So this is the generating function of heap. And now this is a generating function of ordinary pyramid without label, but I have I have the condition M. So how many ways I can label a pyramid having n pieces? The number of ways is n minus 1 factorial. I can put all the label, I have to put the minimum label on the top, and then all the other label I put n minus 1 factorial. So it's an analog to cyclic permutation n factorial and cyclic permutation n minus 1 factorial. So it's exactly the analog. And so you get this now with ordinary generating function. I don't know what. Yes, no, this is this equal exponential. So I put logarithm of this equals this. And now I can put, by going back to the unlabeled heaps, I have this, n factorial divided by n factorial equal n minus 1 divided by n minus 1 equals this. And so I get back my logarithmic lemma. So we made a detour, you see, I made a detour into putting label heaps, putting all your label, and then at the end we take off all the label, but here it remains this, because there is n minus 1 factorial way to label the pyramid with satisfying this condition, small m. Now to finish this class, I will do the logarithmic lemma with exponential generating function in a general form. So you see, I go back, the weight of a basic piece was the weight t power the length, abstract length. There was a function L of alpha, which on my 2 examples, L of alpha was the number of cells of the segment, or number of vertices of each cycle. And so the general form is that, you see, I have a certain heap. Each basic piece, in that 2 examples, each basic piece becomes a subset of a given set capital X. X here is all the projection, all the vertices. I am on a graph. Here I am on the segment of all the integer z. And you see each piece is a subset. And on this subset, there is an F structure. Here the F structure is to put a total order set. Here the F structure is cycle. And the number of elements of the F structure will be L of alpha. L now, which are abstract index, becomes the number of elements of the subset U. And so I take label heap means there is capital N factorial labeling of the heap, which means I am going to put the number 1, 2, etc., capital N on all the cells of all the heap, or maybe on all the vertices of all the cycle. So I take the total number of N will be what was before L of E. Here it will be the total number of elements underlying each subset U. I will call the subset the support of the basic piece alpha. And it's the sum of all the support. So I take, there is capital N factorial labeling. So it's like if you put, suppose you have this heaps of cycle, you will put 1, 2, 3 until capital N, a different label for each vertex of each of the cycle. Before, in the simple case of the logarithmic, I was putting a 1 to n a label for each pieces. Now I put a label for each point component each pieces. And then, of course, I have you can easily see that generating function of Heaps is exponential. Because this is n factorial divided by n factorial, this is n minus 1 divided by n factorial. So I have a species formulation where a pointed pyramid is a pyramid and one of the vertex is pointed. So I can write this like this. A logarithm in terms of a species now of the heap is pointed pyramid in terms of species, and because exactly the same thing. You are labeling all the things n factorial and then dividing n factorial or the right number, n minus 1 factorial divided by n factorial, you get this. You get back the general lemma, but not using the logarithmic derivative, but using the exponential derivative function with species. And I will finish with the second proof by there is an operation pointed species, analog of the operation for ordinary derivative function. The pointed species mean you just take a structure f on the underlying set U, and you choose one of the points. Pointed species, it's a pair, an F structure alpha on the set U, plus the choice of a point X in the underlying set U. And in terms of exponential generating function, then pointing means t times the derivative of F. Well, I am not defining the derivative of a species, sorry, but this is give you an idea. It can be done in species. So to completely understand it, you should follow what is the definition of the derivative from the previous course, and then I will finish that the species of label heaps equips an F structure. See, species of label pyramids. Label means that the pieces on the top has one of the vertex is pointed. So you have a pieces, it's subset of a set X. On each subset, you put an F structure, and I have a heaps of F structure, like the two examples, heaps of cycle, heaps of segment, but I can do this heaps of many things, heaps of permutation, heaps of trees, anything, heaps of the F structure, and then I have the notion of label heaps, label pyramid, and I have this pointed species in the sense of pointed species. This is a pointed species of pyramid, but pointed max means you just point the maximum element of the pyramid multiplied by h, which give you again this logarithmic lemma in general form in exponential generating function. So we have two logarithmic lemma, simple and general, with two different proofs, ordinary and exponential. So you will choose which one you like. And the last remark, which may be like like a puzzle. If you read the appendix of Kratenthaler, so he has this element. This seems to be, this has never been formulated in general form, the logarithmic lemma. Preparing this class, this is implicit in many papers, but preparing this class, I make the effort to formulate it in completely abstracted. But if you read the appendix of Kratenthaler, he is not writing the logarithmic lemma like this. He's putting t equal 1, and it's in fact the weight of the heap. Each species is a letter of the commutation monoid. So it's an equality between here it's a monomial product of basic pieces. The monomial is going to be so, and t, he replaces t by 1. There is no variable t. But look here, what happens if I put t equal 1? See, if I put t equal 1, then this is the same left-hand side, but these are different. So where is the contradiction? Think about this. So which means I have this logarithm. When I take the formal sum of heaps like a product of the pieces, like a word in the commutation monoid, and if I take the second left-hand side as a product, this one, So the letter, maybe, suppose I have the heaps of cycle. The letter can be the product of the letter related to the edges or the vertices of a cycle. And now you understand more. When I work with exponential generating function, the species here, the underlying set, was a set of pieces of the heap, but here the underlying set, each species has its own underlying set. So in terms of exponential generating function, you see there is really a difference. So logarithm would be ambiguous notation when I take just this v of e. So logarithm is related to a variable. Here variable t counting the number of pieces. Here the variable t counting some decomposition of a basic piece into some smaller element. And
one, doesn't it stop being summable?
if t equal 1, you see I have here sigma of v of p. I have two different right-hand side and I have the same left-hand side.
But it's still summable?
Yes, it's still summable. It depends on the weight now. If the weight is a product, if the weight, as Kraten-Thaler appendix, is a product, each basic piece is weighted by its own letters in the combinatorial monoid, then it makes sense. And in my second example, if each heaps of cycle is weighted, each letter is one of the edge of the cycle, it makes sense. And to precisely make sense of this, I give you the last slide. So the last slide is the following. Take a matrix Aij, K by K matrix. Take the weight of a cycle. The product of the weight of the edges. Each edges is weighted A index Ij. And this is the generating function of trivial heaps of cycle with a minus alternating generating function of trivial heaps of cycle. So you put minus 1 power r, sum over all configuration of disjoint cycle, 2 by 2 disjoint cycle with the weight v gamma 1, v gamma 2, v gamma r. So it's an alternating sum of weighted trivial heaps of cycle. And I claim that this is a determinant of 1 minus a, which is usually written like this. We will see, it's an easy exercise in linear algebra. It's equivalent to this. So you see, so determinant, so the inverse of the determinant, which is going to be the generating function of heaps of cycle, will be given by this. But now you see the variable, taking the logarithm of the inverse, is going to be the pointed pyramid of cycle. But here the variable are the letters a, i, j. And for a single piece, I have many variables. In the case, simple case, where t equal 1, the variable was formal letters for each pieces. It's like if I was for each cycle, I put a single letters. Taking the logarithm sum of all this makes sense. But now if I do this, extension of the logarithmic lemma, the logarithm of the sum of the pyramid of heaps of cycle, which would be different, but makes sense also. So which means I can take the logarithm of the inverse of determinant of 1 minus a. It's going to be the pointed pyramid with this weight. All the variables will appear. So I will go, this is chapter 4, I will go to linear algebra, because here trivial heaps of cycle is exactly taking a determinant, taking the inverse, etc., taking the logarithm. This is Jacobi identity, so we will see all this. But you see the difference between the two logarithms. One is related to the variable for each piece, and the other variable is for each piece is decomposed into something more complicated, and each variable is going to be for each elementary part of the maximal piece. So maybe you can think of the contradiction by putting t equal 1, but there is no contradiction. Depending of the when you take the logarithm of a formal power series, it's like taking logarithm of 1 over 1 minus t is sigma of tn over n. Of course, if you take another signification of variable t, you see the tn divided by n, you can compare for the two different forms of the logarithmic lemma that the n are different here. One is the length, total number, the length as a word as a commutation monoid, and the other is the length of the total number of edges of all the heaps of a cycle. Okay, so I will finish here. Thank you very much.